AI gets smarter by getting bigger. This model has 70 parameters, which is not a typo for 70 billion. It learned an arithmetic rule from about 30 examples, then got every answer right out to 1,000. That model is not a neural network. It is a cellular automaton, a strip of colored cells that updates itself by one fixed local rule. Over and over, the same family of system as Conway's game of life. A team from the Wolfram Institute and Ostfold University College calls this framework emergent models. Modern machine learning maps an input to an output in one forward pass. These systems instead learn a starting pattern, then let simple rules run until an answer falls out. Their main test case is called EM43. The tape is one-dimensional and every cell holds one of four values. White is empty background, black is a generic active cell, red is the marker carrying the input and the answer, and blue decides when to stop. The trainable part is a lookup table of 60 entries plus a 10-cell starting pattern the authors call the program. 70 parameters, 140 bits in total. In this picture, space runs left to right and time runs downward, so each row is one tick of the clock. The input is written as a single red cell placed that many steps from the origin, so an input of 10 is a red mark 10 cells along the tape. Everything to its left is the learned starting pattern. The rule fires on every cell at once, row after row. When blue cells become the majority, the system halts, and the answer is wherever the rightmost red mark ended up. Nothing supervises what happens in the middle. The training signal is only the final decoded number, so whatever computation forms inside all those rows was never asked for by anybody. Training is a genetic algorithm, 40,000 candidates spread across 20 islands, mutating the rule table and the starting pattern, and keeping whatever scored better. The tasks are small, things like doubling a number, rounding a third of it, or taking it modulo 4. Training inputs only ever ran from 0 to 30, and the test then ran from 30 up to 1,000. These three panels are the same trained model on inputs 15, 30, and 70. Look at what stays the same. The mechanism it found for rounding a number by 3 shifts the red marker 4 left and 4 down, again and again, until enough blue cells pile up to halt it. Feed it a larger number, and the identical triangle simply grows, taking about 4 times as many steps. It runs a procedure rather than storing answers, which the authors call geometric grokking. Exact extrapolation is the part worth stopping on, because it is specifically the thing standard neural networks are built badly for. A feed-forward network fits beautifully inside the range you trained it on. Outside it, the shape is dictated by the activation function, so a sigmoid network flattens toward a constant, and a ReLU network settles into a straight line. Neither shape can repeat, so a periodic rule like x modulo 4 is not something they represent across the whole number line without hand engineering. The automaton hit 100% on exactly those tasks. Here is a harder rule, doubling the odd numbers and leaving the even ones untouched. On the left, an input of 33 has to come out as 66. On the right, 34 has to stay 34. Same lookup table, same starting pattern, 2 completely different behaviors, and the automaton picks the branch from where the red input mark landed. Now the honest part, and the authors are blunt about it, this is foundational work, and they say directly that they are not proposing a competitive architecture. The moment they went from 1 input to 2 and asked it to multiply it by b, the whole thing collapsed, under 20% on training data and under 10% on test. They cannot even say why. The framework is bigger than that one tape. Anything with memory, a local rule, and a way to write inputs in and read outputs out can be trained this way, including a 2-dimensional continuous medium like this one, where the input enters at the green ports and the answer is read from the blue ports. And they prove something stronger than the experiments show. Fix the rule and the interface, change nothing but the starting pattern, and there exist systems here that can compute any computable function. They call it latent universality. Deep learning learns a mapping. This learns an initial condition, and then lets the substrate do the computing. On a good day, that buys you a rule that holds at any scale, out of 140 bits and 30 examples. On a bad day, you cannot get it to multiply 2 numbers. The authors put this work at roughly where deep learning stood 20 years ago, which reads as either a warning or an invitation depending on how much you think scale was ever the point.